Hi guys, hope you're all well. In today's video I'm going to be talking about the general principles in pharmacology, and this will include how drugs act. I will add some examples, so let's go ahead and get started. So in order for a drug to induce a physiological response, it must bind to a target. So here I'm now drawing the drug molecule and a target. Most of the drug targets are proteins, but not all of them. Some interact with DNA directly, such as antimicrobials and anti-tumor drugs, but for now let's just focus on protein targets. So there are four main protein targets for drug binding. These are receptors, ion channels, enzymes, and transporters. Let's start with receptors. Receptors are pretty straightforward. You've got your drug molecule which is bound to the receptor. This induces an intracellular cascade to occur and allowing a response to happen. So I'm just going to give you guys an example, and the example that I'm going to give is the heart, of course. So yeah, enjoy me trying to draw the heart. Here are some fun facts. A human heart is roughly the size of a large fist. Pretty cool. And the heart beats around 100,000 times per day. But yeah, here's the SA node, the AB node, and your myocardium. So here I'm just zooming into the nodal cells, which contain beta-1 receptors. Adrenaline or noradrenaline bind to beta-1 receptors on your nodal cells and also on your cardiomyocytes, but we'll come back to that. When bound, this activates the GS pathway, which activates adenylyl cyclase, which converts ATP to CAMP, and this increases intracellular pKa. And protein kinase A, as with other kinases, phosphorylates L-type calcium channels, which eventually leads to an increase in heart rate. This also occurs in your cardiomyocytes, but instead of increasing the heart rate, it increases contractility, so increases the force of contraction. So your nodal cells increase heart rate and myocardium increases contractility. This all leads to an increase in cardiac output because we know that cardiac output is heart rate times stroke volume. Stroke volume can be split into preload, afterload, and contractility. But we'll get back to that in another video. Let's move on. So it's important to know the difference between affinity and efficacy. So affinity is the tendency of the drug to bind to its receptor, and efficacy is the tendency of the drug to activate a receptor. So make sure you know the difference between both of them because it's important to use the right terminology in an exam. And you don't want to lose any marks just because you used the wrong term. So let's look at the difference between a full agonist and a partial agonist because there are some differences, and we will go back to the efficacy and affinity terms again. A simple way to explain this is through a concentration effect curve with the agonist concentration on the x-axis and biological response on the y-axis. When an agonist binds to a receptor, the receptor will activate. So here are two curves showing a full agonist and a partial agonist. And I've just labeled the minimum toxic concentration and minimum effective concentration. As you can see, the efficacy of a full agonist is sufficient enough to produce a maximum response, and this is different from a partial agonist, which only produces an intermediate level of efficacy even when 100% of the receptor is occupied. So now we know that a full agonist does not equal a partial agonist. Let's move on now to the difference between a neutral antagonist and an inverse agonist. So here's another graph showing the concentration of the drug against the biological response. So as you can see, a neutral antagonist produces no response and has zero efficacy, whereas an inverse agonist binds to the same receptors as an agonist but induces an opposite response. Make sure you know the difference as they can often pop up in exams. The best way to understand the differences, and for me it really helped when it came to studying, is through the two-state model, which I will go over now. So as you can see, we've got our resting state and the activated state. They both exist as an equilibrium. Usually when a ligand is not present, then the equilibrium shifts to the left and the receptor is in its resting state. However, as you can see from the diagram, an agonist has a higher affinity in the activated state, and the greater the affinity, the greater the efficacy, and thus the greater the response. So an agonist has a positive efficacy. And as you can see, an inverse agonist has a higher affinity for the resting state, and so it has a negative efficacy. And this is really significant when the receptor is constitutively active, and this is when the receptor is activated in the absence of a ligand. An antagonist has equal affinity for both the resting and activated state, so the efficacy is zero, and thus no pharmacological response is produced. Now, enough about receptors, and let's move on to ion channels. Ion channels act as a gateway, so literally just think of it as a gate opening and closing for the passage of specific ions. So here's just a little diagram of a gate to help you remember it. And I've drawn a little sodium and calcium ion trying to get in and out of the gate. Most often, these are voltage gated or ligand gated. Voltage gated channels open and close due to change in transmembrane potential. For example, to reach a threshold allowing for an action potential to occur. Whereas a ligand gated channels require an agonist to bind to the ligand binding site. Make sure you know the difference between both of them, as it's very easy to mix them up and you don't want to do that in an exam. An agonist can also bind to an allosteric site, and you're probably wondering what the hell is an allosteric site? So let's use this simple analogy to try and explain it. Here I've got a plug socket. I know it's weird, but bear with me. And nowadays you've got one to put a USB cable in. Now pretend that the plug is the agonist which you're going to insert in. But at the same time you have another agonist, in this case a USB cable, which binds to the USB bit. And you would call this the allosteric site because they both induce a response, but they both bind at different sites. An example of this are the benzodiazepine drugs. Here is a GABA A receptor where GABA binds to the alpha and beta subunit, whereas benzodiazepines such as diazepam bind to the alpha gamma subunit. So benzodiazepines act as a positive allosteric modulator at the GABA A ligand-gated ion channel. Some drugs can also target enzymes, and they do it in a competitive or non-competitive way. An example of a competitive inhibitor is ramipril. Ramipril inhibits the enzyme ACE, which is responsible for converting angiotensin 1 to angiotensin 2, and therefore reducing angiotensin 2 concentration in the body. Another examples are prodrugs. These drugs need enzymatic degradation in order for them to become activated. An example of a prodrug is L-DOPA. L-DOPA is used for Parkinson's, and the peripheral conversion of L-DOPA by an amino acid called decarboxylase is responsible for the typical GI and cardiovascular side effects when it gets converted into dopamine. Therefore, L-DOPA is usually given with a DOPA decarboxylase inhibitor like carbidopa to prevent the metabolism until it has crossed the blood-brain barrier, where L-DOPA can get metabolized into dopamine and induce its effects in the brain without having any of the GI or cardiovascular side effects. Last but not least, we've got transporters. Transporters are proteins that transport substances across biological membranes. This is usually for molecules which are too polar and thus not lipid soluble enough to penetrate the cell membrane directly. An example of that is water. Water is very polar and therefore requires a transport protein to help it move across the membrane. An example of a transport protein is a sodium-potassium pump, which uses ATP to transport 3 sodium ions out of the cell in exchange for 2 potassium ions into the cell, each against its concentration gradient, and this is to maintain the resting membrane potential. This is often involved in the initiation of an action potential. So now we've gone over the basic principles in pharmacology. I hope you did find it useful. Thank you for watching.